Alright, this is video 2 for atoms and heat. To start off with this one, we're going to talk about the enormous energy in heat. So, we've already talked about how the average speed of molecules is around the speed of sound. But, they're all moving in random directions. So, if we were to make all of the, atoms and molecules move in the same direction, this object would be moving around 700 miles per hour. But it would have the same energy. So, it's often impossible to extract this energy of random motion to do useful work. But the opposite is possible. So, when an asteroid hit the Earth around 65 million years ago, all of the molecules were initially moving at 30 kilometers per second in the same direction. After the impact, the molecule's direction then became random. So the kinetic energy was turned into heat. So whenever asteroids hit planets, all of the organized motion becomes random motion. The amount of disorder, going from order to chaos, we can quantify that. And it's a value that we have called entropy. So, when an object is heated, its entropy increases. Okay, moving on. You may have noticed this, some sort of noise, like a hissing sound in your radio, like if you're between stations, or on a TV set. Sometimes you'll notice like that snow. It's like it's like a black screen with a bunch of white little dots moving around when there's no station. So, what exactly is this? And it's kind of a unique answer. What you are witnessing is electrons. Specifically, the electrons jumping around in the wires, and the electrons jumping sometimes on and off of the wires. And what this shows is that the electrons are in a constant state of motion. And the reason why they're in constant motion is due to heat. Now, heat doesn't have to be hot. Heat can be room temperature. But even at room temperature, there's enough heat energy to keep the electrons moving quite quickly. Now, if you were to lower the temperature, you can reduce the noise, because if you lower the temperature, there's less heat energy and the electrons are not moving as quickly. So in high sensitivity electronics, oftentimes you'll notice that they are cooled. But too much cooling can cause a device to stop operating. Transistors depend on room temperature electrons to work. So we have to, it's a balancing act. Some equipment needs to be cooled, other equipment doesn't. So it's just something that, you have to be careful of, I guess, if you're designing some of these pieces of equipment. All right, temperature. What exactly is temperature? If it's 100 degrees Fahrenheit outside, it is hot. If it's 32 degrees Fahrenheit outside, then it's cold. These are two different temperatures, and we use a thermometer to measure them. But what exactly is temperature? Well, temperature is a measure of the hidden kinetic energy of the molecules. So when the temperature increases, the average shaking energy, the kinetic energy of all the molecules, is greater. We're going to use average because at any given instant, some of the molecules may be moving faster or slower than others. That's usually because of collisions, molecules colliding with other molecules. So if two objects have the same temperature, then their molecules have the same kinetic energy of vibration. So let's take a look at an example then. Let's say we have an iron bar and a copper bar. So iron and copper, two different materials. And let's say they're both at the same temperature. So then that means that the molecules of both materials would have the same kinetic energy. But would the molecules of both materials have the same speed? Well, the answer is no. Kinetic energy is equal to 1/2 times the mass times the velocity squared. The mass of copper is greater than the mass of iron. So, if both of them have the same kinetic energy, the iron molecules must move faster. So, no, they would not have the same speed. So if we take a look at the kinetic energy, if the kinetic energy is going to be the same, if the mass is smaller, the velocity must be greater in order to keep the same kinetic energy. And notice that's v squared. So that's another thing we have to be careful of. So this leads us into the Zeroth Law of Thermodynamics. Kind of funny story. They already created the first law of thermodynamics, and then they discovered this, and they say, hey, this is more important than the first law, so they created the Zeroth Law, just to make sure it's in front of the first law. So a key discovery that makes temperature useful is a simple fact that two things that touch each other will reach the same temperature. And this is how thermometers work. So the thermometer is in contact with the air. So eventually, the thermometer will become the same temperature as the air. Mass has a role to play as well. If the thermometer is initially warmer, has a higher temperature than the air, the thermometer will cool down and the air will warm up. They will become the same temperature. But since the mass of the air is so much greater than the mass of the thermometer, uh, the air's temperature, you wouldn't notice it changing at all. But the thermometer, you would notice it changing. So again, this is called the zeroth law of thermodynamics. So a little graphic here, if A is in thermal equilibrium with B, and if B is in thermal equilibrium with C, that means that A must be in thermal equilibrium with C. So if we take a hot iron object and make it touch a cold copper object, since they are touching, the faster molecules in the iron will bang into the slower molecules of the copper. The iron molecules then lose energy, causing their temperature to drop. The copper molecules will gain energy, causing their temperature to rise. And once both objects have reached the same temperature, the transfer of energy will stop. So heat can be thought of as the flow of energy from a high temperature object to a low temperature object. So, this leads us to another question. Where exactly is our hydrogen? And we've talked about this a little bit before. Hydrogen is the most abundant element in the universe. And yet, there's almost no hydrogen in Earth's atmosphere. So, at one time, Earth did have hydrogen. Because of its temperature, however, the hydrogen had the same temperature as the oxygen and nitrogen in our atmosphere. And because it had such a small mass, it had a high velocity. This velocity matched something called the escape velocity of the planet. And as we mentioned before, escape velocity is the velocity that, if something has that velocity, it will escape the planet and never return, which is right around 25,000 miles per hour. So all of our hydrogen just left the planet. Earth's gravity was not enough to keep the hydrogen trapped in the Earth's atmosphere. All right, the next thing, this is a little cool to talk about, the fate of the universe. One possible fate of the universe is something called the cold death. Stars are hot. Space is cold. Heat is the flow of energy from hot to cold. So eventually, everything will become the same temperature. That's the zeroth law. So, for outer space, that's negative 270 degrees Celsius, 3 Kelvin, or negative 400 something degrees Fahrenheit. That is cold. All right, well, this concludes the second video in the atoms and heat unit.